I will start. Okay, I will start by welcoming you all to this ISPRS webinar. This is the first of two webinars organized by the Intercommission Working Group 2 1B on digital construction, reality capture, automated inspection, and integration to BIM. The working group is composed by Mehdi Maboudi from TU Braunschweig from Germany, Karosh Koschelman from University of Melbourne, Australia, myself, Jonatas Valença from National Laboratory of Civil Engineering in Portugal, and Yelda Turkan from Oregon State University that will share this session with me. It is also important to mention that these events are organized in the scope of a webinar series that are technical supported by the ISPRS Student Consortium, to which we would like to thank for all the support, and special to Lakshmi Thapa. I think now I would like to pass the moderation for my colleague Yelda, who will introduce the first speaker. Yelda.
Great, thanks, Jonatas. It's my great pleasure to introduce Professor Pingbo Tang, who is an associate professor in the Department of Civil and Environmental Engineering at Carnegie Mellon University. His specialty is in computer vision and multimodal data analytics for human AI collaboration in civil systems. And his research leverages remote sensing, photogrammetry, and human systems engineering to enhance the integration of AI in infrastructure operations. Professor Tang is the recipient of NSF Career Award and the prestigious ASCE Daniel Halpin Award. And he's very well recognized for his pioneering contributions to infrastructure intelligence and construction innovation. With that, the floor is yours, Pingbo.
Yeah, could you hear me? Yeah.
Hello? Yes, we can. Thanks.
Great. Thank you, Professor Turkan, for the introduction. Special thanks to ISPRS for this opportunity to allow me to present my work. My special thanks goes to my institution, my collaborator. I saw some of them online, Professor Yilmaz from Ohio State. I noticed that Dr. Yilmaz is here, and a lot of the work is a collaboration. It's not by no means my personal work. So let's look at this decision scenario, which is a nuclear power plant outage control. Outage means a nuclear power plant need to refuel their reactor every 18 months. For one of the reactor in Phoenix, I think it's a nuclear station with a 3 reactor. Every 6 months, there is 1 reactor need to refuel, and the refuel need to shut down the reactor and renovating the structure, check the structure condition, mechanical system condition. It's 20 to 30 days of work. There is a 2,000 plus refueling activity. In the meantime, you can see that there is a large number of workers. The peak time will be 2,000 workers in the field working the same time. It's a pretty complicated process. You can view it as a very complicated construction project with a mechanical system, structure system interact with each other. It's highly uncertain. Sometimes when we find some problems of the mechanical system or structure system, it's a safety concern. And many workers, they need to collaborate and to make sure they're doing the right thing at the right time. Then the safety problem in this case is everybody following the safe procedure in that context, because whenever the context is changing, the procedure could be adjusted. Is that efficient? For this particular case, this nuclear station in Phoenix, 1 day of delay, it's going to cause a loss of around 1.5 million US dollar. So that's the data in 2016. It could be higher for today. Then for this particular scenario, we are saying it's an operation and a maintenance problem of a civil infrastructure because nuclear power plant is a critical component of the electricity generation and distribution infrastructure of the power grid. Once we look into this problem, we can see that there's two types of humans who are getting engaged into the operation and maintenance of the project. The first type of human, they are working in the control room on the left side. You can imagine like for analog room, it's facing control panel with the buttons and meters. They are looking at those things physically. There is a digital control room which is emerging. That's something you can see in Idaho National Lab or some places which is new, like the newly built nuclear power plant. They have digital control room. Those people look through multiple places and look at the screen and to see what are the normal or abnormal readings of the sensors and what are the right time for them to push a button and to execute a procedure. The other group of people, they're working in the field. For example, we need to send out the operator field worker to the site and to check the condition of a mechanical system and to make sure that everything is as what the control panel showed. And sometimes the sensor reading might not actually reflect in the field condition. Now, the big challenge is there is an interaction between the physical space and the cyberspace, and the human in the control room and in the field, they need to collaborate. They need to communicate very well for enable remote operation in an efficient and safe way. So that efficiency, it's important, but at the same time, it's also important for the reliability. We need to make sure that in the control room, the person who is doing the job, they're checking the right thing at the right time, and they execute the command in the right sequence. In the field, we also need to look at the operational reliability of the field worker. They are interacting with the physical space correctly and at the right time, and they are not having misunderstanding between the control room and the field worker. When we go deeper into this interaction between different system and people, we can see that there is this vertical dimension. They recognize things, and they make a decision, and they execute the process. If we go to the interaction between human and physical space, it's a HP. It's like how the worker do the right things in the right at the right time in the field. HH is a communication problem. It's a teamwork problem. And the human cyber problem is like how the people interact with a digital model. For example, today we are talking about the building information modeling. We're talking about the digital systems for control. So that's the human cyber interaction problem. I'm going to go deeper into this and to see if we have a more reliable interaction between HP, HC, and HH, then we should have those like augmenting reality system. Because today, our augmented reality system, sometimes they do not have a sufficient intelligence to tell us, okay, in my field of view of the physical space, what are the right thing to touch? And what is the real-time condition allow me to touch? And what is the right sequence for me to execute the work? So I call virtual label. Virtual label should be generated by our artificial intelligence agent together with a computer digital model integrating sensor data. And with the real-time condition of a nuclear power plant, we should let the operator know which part of the physical space they need to pay more attention, and what is the thing they should not touch, and what is the right timing for them to execute their work order. Then you can see that from the physics process execution side, you can see we can have a broad view to have a virtual labels for highlighting critical relationship between workspaces. We could have a virtual label for highlighting critical object for local view for a person who is looking at a pipe, a sensor meter, and to check the relationship between multiple sensors, are they forming the right pattern. We also could have this control room people, if they are facing too many screens, the system should let them know, okay, you don't have to pay attention to everything. They are going to guiding this attention of the person to the right space and to check the number of people get in and get out. And also from the physical space, they are going to let the worker know the virtual label for highlighting targeting work location. Then the human controller could not be replaced. That's my opinion. We have the artificial intelligence. We can do autonomous driving, but for those kind of open space problem of a large infrastructure problem, we need to have human controller interacting with a AI agent to complete those work for high stake and a safety critical scenario. So this scenario, I just presented nuclear power plant outage. We also could apply the same concept for other scenarios, which also has a control room, has a physical space, such as air traffic control. Then from this one, we can see that we have HP problem, HC problem, and HH problem. Due to the sake, for the sake of time limit, I will give you two quick examples for HP and HC. I will not cover HH, communication problem, which is a much more complicated domain. Someone else, like a Professor Nancy Cook from Arizona State, she has been spent her whole life to do this. Let's take a look at the HP problem. For HP problem, we can see that the nuclear power plant field, they provide the information and the sensor is going to feed into a digital model. And the digital model will have control signal back. Ideally, AI agent should be able to autonomously send out those signals and to make sure that the whole thing is operated properly. But sometimes the sensor data might not be reliable, or it's like a malfunctioning of some devices and which does not align with the sensor reading. So we need a field operator, we need a control room operator. Then the control room operator, they are going to use the experience to guide the field operator to say, what are the things you should check to make sure that everything is okay. Then the field operator is going to check the field and reporting back to the control room person. And the control room person is going to say, okay, everything seems like aligned, then the algorithm should go ahead and do the work. Now, sometimes there is human mistake. I would not say it's an error, but it's not like just the responsibility of anybody, because by nature nothing is perfect. Human could provide inaccurate information from the field, or the control room people will provide a list which is not very comprehensive, and the field operator might have some observation missed in the field. Then we need to have an additional protection. So this additional protection is we could have AI, artificial intelligence, to check the control history and to check compliance of the worker's behavior and the machine systems behavior, and to make sure that they are compatible. So in that way, we can double check, are they doing the right thing, and are they paying attention to the right object? A better situation would be artificial intelligence system guiding the worker to the right location, and based on the machine condition, and also have the human to use the experience to navigating to the right location, and with a double check from the AI. Then the AI will highlight critical object, identify those objects for every step, and to make sure that everything is executed, and for the real-time contextual data, it's okay. Then it's not just look at the current moment, it's also look at the trend. For example, for Fukushima nuclear power plant problem, the trend prediction is a big issue. They need to know after how many seconds these things will change, and if we can do this thing right now, are we able to do it after 5 minutes? So the computer vision, many of you are expert for computer vision and photogrammetry. And on our team, the expert is Professor Arpa Yamas, who is helping us to collecting those information, the video data, analyzing the video data to understand the behavior of workers in the workspace, and to align with the information collected from the mechanical system, and put them into the augmented reality glasses to remind the worker to say where you should go, what you should check, and what is the prediction about the condition after 5 minutes. Then the overall architecture is an integration of digital sensor and digital information models, such as, you can say it's a kind of like a version of a building information model for nuclear power plant. And we combine those two together. That's a term someone has been speak frequently recently. They call digital twin. Then we emphasize the digital twin in terms of human-computer interaction, and to guiding the worker to localize themselves, and to guiding their attention to pay attention to the safety critical object, and to provide them risk information based on the prediction of the system condition and the trend. Then inside this whole system, we need multiple sources of data. That's what I'm trying to say, multi-modal data analytics. We have a sensor log. We have human perceptions extracted from survey and interview. We can look into the inspection report, operation report, accident report through natural language processing to understand what happened in the past. We can also analyzing the video data from the human body and who is observing the environment. Also from the fixed camera in the workspace, observing how human moving in the workspace. Of course, the augmented reality device is going to align humans' location with the physical space to provide people the real-time field of view about the critical object they should pay attention at the right moment. Very quick, sensor logs analysis. This turns out to be a very difficult problem. We look at we try to train the computer algorithm to look at multiple sensors signal time series. And for example, you can see we can look at step 1 to step 5 and to see at what time human has been doing the work like turn on the valve or turn on another valve, and to see how the core temperature and the cooling flow has been changed. Then the idea is, are we able to use multiple sensors time series to train the algorithm to say, this is what happened in the past, and this is the right time for you to push the button, and this is the right sequence to push the button. It turns out to be a very difficult problem. And we use a black box algorithm, we cannot achieve very high F1 score. And we are still trying to use ontological explainable AI to do the work. And so far, we only achieve F1 score 0.323 without explainable AI. So that means we have to have a very, a lot of work to do to apply new algorithms to understand if we use the sensor data to predict what is the right thing to do at what time, how to augmenting human explanation about what they're doing and how they choose the timing to push a button and how they choose the sequential observation and the decision-making process to make sure that the process is safe and efficient. It's still a long way to go. We haven't done that yet. Now, to make it explainable, we have to have some semantic information to help us to understand what happened in the past and what we should do. So let me dig into a little bit about those explainability. And this is a picture to show how the explanation from the nuclear power plant licensing event report, you can view it as an accident report to documenting what has happened and how people do the work to address the problem in the field. And there is, of course, those regulation guidelines. Those are the manuals guiding the worker to do the work. Then these two parts are natural language like a data. And we could use a natural language processing to align the information from the natural language processing algorithm and to understand what is the explanation of the real-time data and what are the explanation of human activities to address the event happening in the field and in the mechanical system. So this is one of my students' work, Dr. Jingding Xing. She has been looking at the integration of ontological modeling and develop a representation schema to support function reasoning of the nuclear power plant with some reasoning capability to identify and explain the sensor data. And in her ontological representation, it's a template to classify object, which has been represented in the digital model of a nuclear power plant as component, connection between component, and the state of those components, as well as what is the active state and what is the passive state, and what are the time people should be able to push the state of the machine from active to passive, or vice versa. So from the historical data, we have those operation procedure and the natural language processing algorithm. This is much older, and it's like a 2020 time at that time, 2021. We use our BERT algorithm to process the operation procedure and to generating a work package database and to producing conditional conditional guidance for the worker to say, what is the condition you should observe before you execute this work order. Then the new challenge here is we recently worked together with Westinghouse, who is developing the microreactor called ISPRS program. They are trying to get the license right now for making the nuclear power plant much smaller for future generations of electricity infrastructure. Then the natural language processing and ontological models we developed is for the last generation of a nuclear power plant. It's called PWR, pressured water reactor. And we want to translating the accident report, incident report, and operation experiences for the last generation, and to see to what extent we could reuse the operation guideline and experience to the new generation. We should be able to identify some common function and a common problem, like a cooling system problem, even though they are using different cooling system design, but physically, they are trying to cooling down the reactor, the core, and to figure out what are the possible ways to reduce the temperature, and what are the mechanism is aligning with between two type of system, and how the worker should be able to transfer their knowledge from the last generation of the reactor to the new generation. So this is ongoing work. We are trying to transfer from the traditional nuclear power plant regulation to eventually microreactor. At the system level, we look at how many components we have for the for this larger and smaller nuclear reactor, and to see which concept align with each other, so that we can reuse some of those guidelines and the inspection procedure, checking procedure, and operation procedure documented in the past. So this is a definition used the ontology to define the entity, state of affiliation, and the causal from the regulation, and to provide the basic boundary condition for safe operation. And this is the next step. We are trying to build a knowledge graph. It's ongoing work, and to use the guideline and to understand from multiple guidelines published in the past, could we generate a knowledge graph to regulating the operation procedure, and to help the worker to explain what they should do, what they should not do, and why. Then this knowledge graph, we go deeper into them. It's like we are at the moment of see from which regulation and what they are discussing, and what are the procedural items are related to each other, and how they are regulating different parts of the mechanical system. Then put human in, and we're going to say, okay, who are the people, like the supervisor or the field manager, and what they're doing, and why they're doing this, and based on which item in the procedural definition. Then we need to go back to the field and to see, are they really doing the right thing? And we're using computer vision algorithm to help us to check, are they at the right location? You can see positioning the worker. If a person, this is Professor Arpa Yermas's work, and we input the floor plan, which is a building information model, and we have the camera on the human body and to observe the environment, and we have the inertial measurement unit, IMU, to tracking the acceleration of the person moving in the workspace, to locating based on where you are, based on your observation, and align with the building information model to estimate their current location. Then we are going to give them the information to say where they should go, and what is the probably the most critical workspace and the critical component they should pay attention. So when they are moving, and it's a navigation process, to have the camera continuously monitoring their location, and have the work order to check against the workspace, and to say, are you arriving, or you should go further. Then once they route to the site, it's going to have object detection network and check with the camera video to understand which object they are looking at is the right object to touch. So this whole thing, it's a worker location, safe path planning, critical object detection. And we have Professor Yerma's group at Ohio State University to develop the integration of the real-time camera on human body, and to utilize a few target, I call chessboard, right? To indicating some rough location of a critical object along the way, so that we can calibrate the localization results from the camera only, and we use the IMU camera and those target information to improve the localization accuracy to tracing the human location in the workspace. With those tracing, then we need to provide information. So those information, it's related to another work has been done by Professor Xiong, and he is a professor at Kent State University now. And we're looking at an open construction data set. Actually, some of the data set is from the construction domain from University of Alberta, Professor Xiaobo, and who is in Michigan Tech right now. And we are comparing how those data sets could be augmented by our taxonomy for classified construction object, and to generalize how different things, even from different data sets, they have a different name, but they essentially, it's about the same safety problem. Then from there, we can trace in human activity and the human body, and to understand if you accumulate some operation knowledge from one workspace, how you can translate that operation knowledge to another space. And in this case, we are using this human body tracing algorithm to check where they are and which part of the human body it's violating or follow the regulation, the safety constraint. Put them together, let's rethink. We have Markley's AR for nuclear power plant field operation, and we could have like a digital information model to drive the Unity engine to simulate what's going on in the field. And we need to have the natural language-based work package information extraction. And we have the Bayesian filter-based real-time worker locating to provide information for the worker to understand what, based on the real-time situation, where they are and what they should do. I will give because of the time limit, I will give a very quick example for the control room because we just finished the field. For the control room, I'm going to use the air traffic controllers example. We have those accident in January from DC Reagan Airport. So that problem is actually because of the ATC. They only have one ATC, and the communication between the air traffic controller and the pilot has a small problem, and the landing problem caused like a situational awareness misalignment between the pilot who is driving a helicopter, and also the situational awareness of the person who is driving the American airline aircraft. Then one thing we have been doing in the past few years is to tracing the talking behavior of the people who are communicating with each other for locating where they are and what is in the neighborhood. And we want to timely recognize those abnormal situations and to help preventing the loss of separation between aircraft. We did some experiment with a 6 experienced ATC with a simulator at Arizona State University. Professor Nancy Cook, she is the major person doing this research. And we did the experiment with a baseline situation, high workload situation, and high workload off nominal simulation, nominal situation. For the high workload, the only difference is like we have more aircraft in the sky, like 30 in total. The difference between off nominal and the high workload is they have distractions. Distractions, for example, the weather condition influence the path of the aircraft, or the runway allocation has been changed, and you are supposed to go to another runway, not this one. So we did a lot of experiment, and this is multi-modal data I mentioned before. And I would like to emphasize the importance of not just using computer vision. We need to augmenting computer vision with multiple sources of data like ECG headset to measure the heartbeat interval. And we also need to have the sensor data to tracing the location of many aircraft from that GPS signal, and use the video data. Of course, we can trace the head pose, eye movement, facial expression of the person, and to understand how complicated is the situation and what is the person's workload, and how likely they are going to make a mistake. Then this is the bigger picture. we need to know what is the complicated task, to what level complicated task with very dense traffic, with off-nominal event is going to influence the cognitive workload of the person and to influence their likelihood to produce operation performance. Loss of separation means two aircraft getting too close to each other. And our experiment actually showed that the off-nominal situation, which is number 3 here, you can see that the workload, the vertical axis is the workload, and it does not increase too much, increase slightly compared with the high workload. So what that means? That means even though we have some distractions when people are very busy doing their work, some tiny distraction doesn't influence their mental workload too much. And we also tried our LSTM algorithm to analyze the facial expression time sequence, heart rate time sequence, and also the head pose time sequence, and to see if there is any patterns of human behavior can help us to predict these are more likely sequential behaviors going to leading to some mistakes. This is some very quick result I'm going to conclude very soon. We can see that if we want to predict in the next few steps how likely humans are going to make mistakes, we can predict further and further away to the future. One step in this case is 5 seconds. What that means here is that 2 steps we're predicting what's going to happen in the next 10 seconds. 10 steps means what's going to happen in the next 50 seconds. Of course, if you predict further in the future, the precision is going to decrease, and repeat the algorithm many times for a few scenarios. Plus minus means sometimes the algorithm is better. In some situations, the algorithm is not so good. So plus minus is the fluctuation of the performance. So statistically, we can see that for 2 steps, which is a near future prediction, we don't need a heart rate. And for further away to the future, heart rate actually contribute to the accuracy. Conclude. The main problem, we look at the historical data, regulation, real-time video data for computer vision. And we are looking for real-time support system for the operators of civil infrastructure, such as nuclear power plant, airport. And we want to have an intelligent real-time interpretation for the human to understand what's going on in the field and what they should do now. Back to this, we have a building information model, and we have a human data. And we need to recommend what is the safe, healthy, and efficient operation plan. And we also have simulation to predict for the next few minutes what's going to happen. Thank you. Sorry, I'm over time. Sorry.
No, it's perfect. Thank you for your excellent presentation. I think now we will move to our next speaker, and in the end we can have the Q&A session. But I invite all the attendees to, if they have any question, they can start to put it in our chat or Q&A to start to see the questions and collect the most relevant and to prepare our Q&A session. So right now we can move for our second speaker. I have the pleasure to introduce Jiansong Zhang, an associate professor at Construction Management Technology at Purdue University. He has a relevant and pioneer work on invariant signatures in AEC, and he is the founder and director of Automation and Intelligent Construction Lab, which develops scientific theories and methods and advanced technologies to support construction, engineering and management, and construction automation, and also founder and director of Digital Twin and Robotic Automation Center and Knowledge Sharing, Entrepreneurship and Research. So, dear Jiansong Zhang, the floor is yours. You can share and start your presentation. Thank you.
Thank you, Yonatas. Am I audible here? Am I audible?
Yes. Yes.
Perfect.
You are, but we don't see your screen.
Yeah, your presentation are not.
Okay, 1 second. Let me put it back on the screen. Can you see my screen?
No, it's we are just seeing the camera, and your web camera and your face.
Try to share my screen here. How about now?
Oh, now it's
It's
okay.
good now. Yep.
Okay. Thank you so much. All right. So my topic today is empowering the seamless and universal beam interoperability with event signatures or AEC objects. And the main issue or the main problem that we're addressing is beam interoperability, obviously, which is it's a billion-dollar problem at least, because in the current practice, the ecosystem is there are many different software providers, and each of them tends to try to establish their own ecosystem, which may not have a very smooth conversion and data transfer with other software that come from another ecosystem. Which cause a lot of need of manual efforts in terms of the data reentry or even recreating the model for different tasks, such as structural analysis, such as energy modeling, etc. So with the establishment of the industry foundation classes standardization, which is ISO standard for those of you not familiar. So this is an international standard that was developed by the Building Smart, but now this has been adopted in many different countries and regions across the world. The idea is that with this standardization, they would like to see better interoperability between the different BIM software, right? So with that being said, we would like to take a look at some example IFC data. Again, the IFC data is the international open and transparent standard. It's an ISO standard as well. So which means that you can literally open the IFC model with a text editor without the need of any other software, right? So that you can access the data very freely. And in figure 1, we are showing a very simple representation of a line, basically, right? Well, we call it curve 2D in the IFC context, but essentially 2 points define a line so that you can see this 8431, that is a shape representation of this line, of this curve 2D. And then it refers to this polyline, which is 8430. And then the polyline further uses 2 points to represent the line, right? So the 2 points are represented by the first 2 lines here, 8428 and 8429. This very straightforward, no problem, right? Easy to understand. But when it comes to 3D representation, there are several alternative ways to represent 3D objects. For example, there's something called extruded solid, which means you extrude a base plane along another direction that is typically normal to that plane, so that you form a 3D. Or there is another method called boundary representation, in which case you basically grab a bunch of surfaces and use them to enclose a 3D space to form a 3D object. What we are showing here in figure 2 is a method using clipping. So what is clipping? Basically, you take 2 objects in 3D and use one of them to clip into the other, okay? So if you look at this 24593, this item here, it's called the IFC Boolean clipping results. And the attributes are telling us this is taking the difference between 2 3D objects, right? Because you are using one to cut into the other. And if you look at these 2 parts, one is the 24580, which is extruded area solid. So if you remember, this is one way to represent 3D object. Basically, you can use a base plane and then extrude it in another direction to form a 3D object. And then the other one is called IFC polygonal bounded half space. So the polygonal bounded half space is essentially you can use a polygon, basically a 2D shape with multiple sides, right? A polygon, and then you can use that polygon to bound what's called a half space. So what is a half space? Half space is essentially you cut the whole universe into two parts with a plane. Okay, and then you get two what's called the half spaces. So you may use the polygon to form boundary on one of the two half spaces, so that you essentially you get a 3D object with indefinite volume, right? If you think about it. All right. So now, with that being said, I think a diagram here can help illustrate this idea a little better. So basically, if we look at this figure on the top right, we can see the plane that is represented as the red boundary, the red color. So this is the plane that is used to cut the universe into two halves. Okay, so that you get the half space on the top, and then you get another half space at the bottom. And then we have a polygon here that is, you can see the blue lines that are representing this polygon. You can use this polygon to bound the space, right, in this half space. So now the question is, which half space are we looking at? And I would like you to really follow me very, closely here. If we look at the attributes of this entity, the FC polygonal bounded half space, the very first attribute here will be the FC plane, right? So as I mentioned earlier, this is the plane that is used to cut the universe into two. Okay, so then you have a half space on the top, you have another half space at the bottom. And then there is another attribute here, which is 24591, which is called FC axis 2 placement 3D. You don't need to know the name, but basically this is representing the placement. Okay, so this FC axis 2 placement 3D is the most commonly used entity to represent the placement of a 3D object in the 3D universe. And then we have this 24586, which is a FC polyline. So this polyline is representing the baseline, the base plane for the extruded area solid, right? The the 3D object that is cutting into the half space, or in other words, that is the polygon that is being used to bound one of the half space. So now the question is, we have another binary variable here, which is true or false. And this binary variable is used to tell us which of the half space we're looking at. Okay, and if we read the specifications from the Building Smart, it says, if this variable, this is called agreement flag, if this variable is true, then the subset or the half space that we are looking at is the one that the normal points away from. And if the agreement flag is false, then the subset is the one the normal points into. So now I would like everyone to put into the chat. Now you see this variable, the value is true. Do you think we are representing the top half space or the bottom half space? Maybe take a couple of seconds, right? Let me see if I can see the results somewhere. Okay. Seems I cannot see the results, but anyway, there is some ambiguity actually in the description here, right? Because the meaning of this agreement flag may actually arise for two reasons. There may be confusions. Number one, normally in our common practice or common knowledge, the true is used to refer to the positive case, right? So which means the direction the normal points into. And point number two is the potential ambiguity of the phrase away from, which is caused by the unbounded nature of the half space, because both of the positive case and the negative case seems reasonable to say it is the one the normal points away from. Considering that in the positive case, the half space can be regarded as the departure of the normal. And obviously, without rigorous testing, such doubts are not easy to get cleared. So how can we clear such doubts? We can apply a data-driven approach. Let me move to the next slide here. Another problem that is, related to the interoperability is that even for the very fundamental 3D representation of an object or of a project, as you can see in figure 3 here, they can render very different results in different, let's say, BIM software or BIM platform. Okay, this might be surprising because the 3D representation of the building information modeling is supposed to be the most mature and developed parts, right? But however, you still see the interoperability problem. So a couple of years ago, we have taken this IFC data and IFC schema with some due diligence. We can actually generate the systematic understanding of the IFC schema in a much clearer way, which can help us further develop, BIM utilities and tools to analyze the IFC data. So we did a very small experiment by taking a very simplistic bridge model with 4 piers and 1 deck, and try to build a visualization algorithm, right? So as you can see in figure 7, at the beginning, we start with visualizing one of the bridge pier, which is relatively straightforward, by analyzing the 3D representations of the FC objects, right? Which is shown in figure 8. We're not gonna go into detail. But then if you look at figure 9, we can see that, okay, the bridge piers at the beginning, the visualization actually show them not really attached to the bridge deck. And that was because at the beginning, we didn't really take into consideration the IFC axis to placement 3D, which was the entity used to represent the placement of the objects. Okay, so then with that testing, we identify, okay, we need to take that into consideration. So we did. And then figure 10 shows after that, we can successfully visualize this bridge. And at the same time, we can also generate much clearer systematic understanding of the entities in the FC schema that are used to represent the 3D shapes, the 3D geometry, which are shown in figure 11 here. So in the end, with this iterative, data-driven development and refinement, we were able to create a visualization algorithm that is comparable to the commercial platform. So you can see the results from our visualization algorithm on the top and a commercial platform visualization at the bottom on a duplex apartment building project. All right, so now I would like to introduce the invariant signatures idea. So first of all, what is a signature? A signature is something to uniquely identify individuals, right? So like what you can see on the top, there are a couple of different signatures. Those are by different individuals. And we would like to apply the same idea to our AEC domain, more specifically to try to address the BIM interoperability problem. So then we would like to see, okay, what kind of features can be included in these signatures so that they can be used to uniquely identify the objects, right? So obviously the geometry is part of it. So we have the 3D representation, the 3D shapes. That's the first category. And then the second category, we also need to look at the locational information, right? So this is where is one object in relation to another object. And the third category is those material and mechanical properties. So this is the definition that we have created. So invariant signatures on an AEC object, we define it as a set of intrinsic properties of the object that distinguish it from others and that do not change with data schema, software implementation, modeling decisions, and or language cultural context, which means it doesn't matter, which part of the world this is being used, right? So any language cultural context, invariant signatures can be applied. A wall is a wall, a door is a door, right? Whereas the invariant signature should uniquely describe the object and provide all the information needed for the various analysis. So with that being said, we would like to introduce the geometric signature. If you remember, this was the first category of the 3 categories of features that we would like to include in the invariant signatures or object. And let's look at this cone frustum shaped bridge pier, which we use it to start building our visualization algorithm that we have seen earlier. And the first question we'd like to address is, okay, if we would like to come up with the invariant signatures for this Cohen-Franzen shape, then we need to know what are the features that help define this Cohen-Franzen shape, right? And these are the three rules that we came up that govern a Cohen-Franzen shape. This is based on its geometric signature. First of all, the top and bottom faces are circles. And then the second one, the top and bottom faces are in parallel. And the third one is the axis of the shape is perpendicular to the top and bottom faces, right? So this is very straightforward. Now, however, we would like to implement those rules because we don't just define the invariant signature. We really want to use it to help us distinguish a Cohen-Franzen shape, right? Whenever an object came up. All right. Then from the mathematical definition, we can define a circle, right? Which is which is shown in the equations here. Because a circle is basically a shape that all points on the boundary of the circle have the same distance from the center of the circle. So we use this definition to identify a circle. To find the center of the circle, we use the equation 1. As you can see, we take all the points, the x, y, z coordinates of all the points, and then we take the average, right, of all the points to find the center, or we define this as the center, right? And after that, we use equation 2 to measure or calculate the distance between each and every point and that center that we came up with. So now, if this shape is a circle, then guess what? The distance should be the same, right? But the problem is, how do we define the same, or how do we define the distance being equal? So the XYZ, as mentioned earlier, the XYZ in equation 1, equation 2 are the coordinates of the center that we find. And then the XI, YI, and ZI are the coordinates of the different points in this 2D shape, the polygon. So the distance check was conducted by comparing the distance from all the vertices, all the points to the center. And in this case, when we apply this to the Cohen-Franzen shape in our experiment, we actually found that a circle is not represented by indefinite number of points. It is actually approximated by, in this case, 16 points. So then it is in reality a hexadecagon, right? It's not really a circle, it's hexadecagon. It has 16 points. And theoretically, the distance between each of the 16 points and the center should be exactly the same. But in reality, in the implementation, in the computing algorithms, this was not the case, right? Because you cannot, enforce the indefinite number of digits after the decimal points. So that means we need a tolerance. The tolerance was needed to help us implement this algorithm, right? So how can we come up with a tolerance? Well, we look at the data. So the distance from each of the 16 points to the center, we analyze that, and then based on observing the differences between the 16 distances, we can find, okay, what can be the variations in that distance, right? So this is the results that we found from this simple Cohen-Franzen shape. As you can see, when it comes to a couple of digits after the decimal points, the value starts to change, right, to be different. So based on observing this data, that we define the tolerance of the error to be 0.00001 plus minus, okay? And then when it comes to the second rule here, the top face and the bottom face must be in parallel. This is, again, a well-established, formula from the geometric studies. You can see that in equation 3, the x, y, z again are the coordinates of any point in the shape, and then a, b, c, d are the 4 parameters used to define a plane. To decide these parameters for the hexadecagon of, if you remember, we have 16 points, right? 3 points were randomly selected from the 16 points, and then the parameters a, b, and c can be solved by plugging in the coordinates of the 3 selected points. And after plugging in the solved A, B, and C, we can then solve the value of D by grabbing any other point from the 16 points, other than the 3 that we have used to figure out A, B, and C. Right. And then the third rule was there must be the axis, the line that connects the center of the top and bottom surfaces, and this line must be perpendicular to both surfaces, right? So we frame it as the criterion 2. If the top and bottom faces of the convex system shape have the same size, or in other words, these 2 circles have the same radius, then the convex system shape sort of reduced to a cylinder shape, right? So, you know, it's still a convex system, but it's a special case. It's a cylinder. So then with those algorithms developed based on this very simple convex system shape, we have successfully tested those on 3 bridge pairs from other online resources. And there is also a limitation that we have observed, right? Although the testing was successful, the error tolerance that we have set based on the first convex system shape was actually arbitrary. This was based on just this object that we observed. And also we used you know, absolute values instead of relative values, which I'm gonna explain later. All right, so the error tolerance in the equidistance check was described by taking the maximum rounding error observed, if you remember. So although it was tested to be successful in the testing data, it may not be the case in all the possible testing data in the future, because such rounding errors actually depend on the software used to create the model, as well as the parameters and configurations chosen by the modeler. In the ultimate classification algorithm that we would like to see that it includes sub-algorithms for all the known categories of objects, a good estimation of this error tolerance may be obtained by analyzing a large amount of training data. Also, the use of relative value to represent error tolerance may be better, maybe more robust than the use of the absolute value, right? If you remember, we have used 0.0001 plus minus. But you know, this depends on the range of the absolute size of the dimension from the training data that we have used. So, for example, when comparing 2 data values that are close to 0, then their relative distance can be large, where the absolute error still stays small, right? This is bounded by the you know, the 2 data values. And the same rationale can also be used in comparing the absolute value with relative value for error tolerance. Applies also to the relations used in the patterns of the sub-algorithms. For example, the relative relations are expected to be more robust than the absolute relations. The relative relations, such as the parallel relation between the bottom and top surfaces of the convex system shape, it can be more robust potentially than the absolute relation, which means basically it's horizontal, right, between each surface and the world coordinate. But if certain assumptions are known to be valid, such as in real world, our structures usually stand up, right, vertically, then the absolute relations may be preferred because they are simpler to implement and simpler to use. But however, this may not be the case always, right? So it really depends on the context. And on this slide in table 1, we would like to show the geometric signatures for a rectangular parallelepiped shape. So we have came up with 9 features as components of the invariant geometric signatures. As you can see in the first column of the table, we have the number of subcomponents, the number of faces, cross-sectional profile, extrusion direction, the dimensional ratios, number of straight lines, boundary line, connection angle, boundary line, length type, and the turn directions. So essentially, for each object, we would like to come up with the value or range of values for each of these features, right? And those can help us define that object. Similarly, this is the geometric signature for a cylinder shape. again, if you remember, cylinder shape is a special case of the column shape, right? But still, we can come up with the different types of value ranges for the 9 components or invariant geometric signatures. And as you can see, some common objects in our AC domain that are of the cylinder shape include footings, columns, beams, and the table 3 shows the geometric signatures for ring shape, and table 4 shows those signatures for an I shape, which again is a very common shape if you think about I-beams and I-columns. So then figure 1 here shows the cross-sectional profile of an I shape, and figure 2 shows the cross-sectional profile of ring shape. After the geometric signatures were developed, we extracted the features of 1,252 object instances from the collected data. In addition to show an example of the data set, we also developed a rule-based algorithm for object classification, because that is our goal, right? How to use the invariant signatures. We tested the object classification algorithm on 389 object instances from an architectural model. So the algorithm used all the parameter values from the 14 features and successfully classified 336 object instances into the correct categories of beams, columns, footings, slabs, walls, and this overall accuracy was around 86.38%. And we also posted the data collected on the Purdue University Research Repository, which is openly open source, so it's available. So this shows example rule-based algorithm to help us classify an object into different types of beams. So you can see we have covered I-beam, C-beam, and we also cover slab, column, footing, walls, different types of objects, right? If you recall earlier, we have mentioned, first of all, in the FC representation, there are different types of 3D representation methods. We have boundary representations, B-rep. We have clipping, which we have seen an example before. We have swipe solid. This is extruded area solid, where you extrude a plane in another direction to form a 3D. We also have mapped representation, which you map one 3D into another 3D. And constructed solid graphics, which is about composition of multiple 3D objects together in some way, right? So our algorithm will process each of the alternative 3D representations differently, and then for each of the representation, we identify those invariant geometric signatures, and then the algorithm can, based on the value and value ranges of those signatures, can decide which type of object it is. All right, so these are just some example types of beams. We have C-beams, U-beams, I-beams, L-beams, etc. that were covered in our study. And table 6 and table 7 shows these features used to help us identify the different types of beams, right? Because this is at a finer level of granularity. If you think about the level of object classification between walls and columns and beams, and the classification between U-beam, C-beam, and I-beam, this is an even finer level of granularity. But through our experiment, we actually found when it comes to a finer level of granularity, our invariant signatures can work even better, which means the accuracy can be close to perfect. And we also develop algorithm to identify a truss. And when it comes to a truss, it's not just one simple 3D object, but it's a composition of multiple objects, right? Because you have the web, you have the flange, and the different components, and you need to take all of that into consideration. So the algorithm on the right shows how we decompose these truss into different objects and try to identify each type of object. And once we identify each, in the end, we'll be able to tell, okay, overall, this is truss. All right, so in another experiment, we have collected 1,891 objects, and we use 1,325 for training, which is 70% of the objects, and 566 objects for testing. And in the categories of beams, slabs, and wall, we achieved 100% recall and precision. And however, we have notified the low performance in the columns and footing category, right? You can see the recall of footing is pretty low, and the precision of column is pretty low. Guess what? That was because the geometric shapes of these two objects are very similar. They're pretty much just cylinder shapes, right? So which means, the shapes of these footings, or we'd better call them foundations, in the experiments were similar to the columns. And that was why we incorrectly classified them into columns, which means the geometric signature itself sometimes is not sufficient when it comes to the similar shapes between different objects. But we can address that by adding the locational signatures, right? Because the foundations will be usually below ground, and the columns will usually be above ground. So that can easily resolve that. So we take the invariant signatures methods and concepts and the algorithms that we've developed, and we try to apply it to some real scenario between architectural design and structural analysis. And in this case, when it comes to structural analysis, the material and mechanical properties of the objects will be important, right? So we have to include those into the consideration. So in addition to the geometric features, including the shapes and the location that we have mentioned earlier, now we also have the material properties listed here, such as the mass density, Poisson ratio, shear modulus, thermal expansion coefficient, compressive strength, and Young's modulus. So we take this 5-step method. First of all, we define the problem to be between the architectural model and structural model. We would like to see the automated conversion, right, directly from the architectural model to the structural model. To achieve that, first of all, we collect the data for both types of models, and we process those models using our invariant signatures theory. We generate those invariant signatures features, and then we train and test invariant signature based, machine learning and rule-based algorithms to try to help us perform that conversion automatically. And this can be an iterative process because you never get it right the first time, right? You got to improve it over time. So after a while, when the performance is relatively stable or meet our predefined criterion, then we can take it to the final evaluation. So figure 5 shows the simple models that we have used for the development of those conversion algorithms. You can see these are some very simple 1-bay or 2-bay structures with or without slabbers walls. And then we use slightly more complex models for the testing, right? Just to challenge our algorithms. And figure 7 here shows the results side by side. On the left-hand side, this was we call it the gold standard. In reality, this was the manual converted structural analysis model from the architectural model. And on the right-hand side is the automatically converted, structural analysis model by our algorithm. So as you can see, our algorithm actually achieved a pretty good, consistent results with the gold standard by this side-by-side comparison. And then we also took it to a real project. So this was a 2-story penthouse reinforced concrete commercial building. The building is for a medium-sized grocery store. Is 31 meters and 31.70 meters long and 21.60 meters wide. And due to the topography limitation of the building site, the first story is a semi-basement and used as a storage place. And then the second story provides the main shopping area. The results of this evaluation are shown in table 9 here. So as you can see, ultimately on this real project evaluation, our conversion algorithm achieved relatively good precision and recall, right? Both above 90%, the precision is 98.4%, recall is 94.9%. So it's a pretty good results, which means we can actually leverage the invariant signature-based conversion algorithm to help us create the structural analysis model based on the architectural model. So you don't have to restart or create it from scratch every time. But however, because the results were not perfect, so we looked into the errors to see what kind of errors we had. one scenario is there were some incorrectly generated slabs because of their stair openings. This was simply because this was not in the training data, if you remember, right? In the training data, we only have some simple 1-bay and 2-bay structures with or without slabs and walls. We didn't have the staircase. So then it's just an issue of, okay, once we add this scenario into the training data, we will be able to cover it. And another similar case was when there was a slab that actually extended beyond the column boundary, like what you are seeing here. This was also not covered in the training data. So again, the solution can be simply including this scenario into the training data. So to conclude, just for the sake of time, we have an invariant signature theory with initial geometric and material signatures that can be used to capture the essence of architectural engineering construction objects to be used in the various engineering analysis model exchange tasks. So we don't have time in today's presentation to cover the other scenarios, but we actually already tested it in, let's say, interoperability between architectural modeling and cost estimation, between architectural modeling and building energy modeling and simulation, between architectural modeling and building code compliance checking applications. So we have already tested in various scenarios, and we all achieve very good performance like what you have seen. So the theory goes beyond the state-of-the-art or AC information representation, which was based on mainly the data schema, and it enables the robust AC information representation, which is ignorant to software implementation, modeling decisions, and our language cultural context. So this advances the empirical knowledge as well in the area of BIM interoperability by offering a new data-driven method to use invariant signatures for solving practical problems in BIM applications, because this can support the many-to-one paradigm of BIM interoperability and brings the seamless and universal BIM interoperability one step closer to the reality. This theory or this theoretical and empirical knowledge in the area of BIM interoperability can also support an improved model exchange between the different AEC processes and different stakeholders. So with that being said, if you're interested to read more, we have a website that has tallied all the publications and the testing results in different scenarios that I have alluded to earlier. So these are the references. And thank you for your attention.
Thank you very much for your great presentation. I think right now it's the Q&A part is open. Me and Yelda, we are here to try to help. There are some questions already that in the Q&A chat. Some of our first speaker already answers some of them. Regarding, for example, that the last presentation from Johnson, I think, for example, Halper Hilmas that put us some questions regarding give the thanks for the talk that I'm also joined to that thanks to that good talk. And they ask if you had also looked into implicit representation that are used for 3D human body modeling, such as signed distance, transform generation, level set representation, for example. I don't know if you are also
I can see it.
Okay, you can see it. If you want to answer, please.
Well, thank you, Jonatas. This is a very interesting question. So just a little bit more background of why did we come up with invariant signatures AEC objects? So obviously there's a need because the interoperability has been a problem that has baffled our industry for decades, right? This problem actually I learned it when I was a master's student at Carnegie Mellon University and sitting in Professor Berkeley Akinchi's class. That was the question she asked. what was the most important problem currently in the industry, and the answer was interoperability, right? So it has been a very important problem, but currently or back then the state of art really just addressed it from two main angles. One is through standardization, such as using industry foundation classes, FC, and the other consideration was through semantic modeling, right? So you try to develop ontologies to try to capture the different types of objects. But however, let's say the FC standard was great, it's by far widely accepted as the most promising solution to the beam interoperability. Whereas because FC was designed to be comprehensive, so it builds in certain level of flexibility. For example, you may actually represent any object using what's called FC building element proxy, right? If you do not have a designated concept for the object. And because of the flexibility, then that means every software implementation can still implement the FC standard in different ways. And so that actually countered the initial idea or purpose of enabling the interoperability. So then we try to find, okay, can we actually look at the objects themselves rather than relying on standardization or semantic modeling, right? So then what inspired us was actually those theories from the computer graphics domain, such as the SIFT features. For those of you who are familiar, with scale invariant feature transform, which was the groundbreaking discovery in computer vision that has enabled the vast amount of developments, after that, right? But because prior to that, you could only do limited things in processing images. So then we borrow that rationale, right, and try to apply it to the AEC domain to come up with the invariant signatures. So the reason I mentioned this background was because I think to answer Alper's question, I believe this can be applicable, or maybe a better term to use is adaptable to other domains, such as modeling human bodies, as Alper has pointed out, and modeling any complex shapes, because the shapes are stable, right? Human bodies are all in similar shapes. We all have arms and heads and the trunks and different components. So I think it's similar to, let's say, a truss where you have the web and the flange and the different components, right? So I believe this can also be adapted to modeling a human body or other types of objects. It's only that when you look at the components or the detailed features, you may need to have slightly different variations from the feature that we have used for engineering objects, because the engineering objects tend to have pretty regular shapes, straight lines, right? Whereas human body is full of curvatures. So I will predict the invariant signatures for human bodies will be way more complex than the invariant signatures for an AEC object, but that is possible. Okay, there's another question as well. How do invariant signatures? Yeah.
Sorry, go ahead, Johnson. Yeah.
Oh, thank you, Yada. How do invariant signatures handle complex parametric objects with different geometric representations across various beam platforms? Are there any considerations in different scales? Excellent question. This directly hits some of the points that I mentioned in the presentations, right? So when it comes to complex parametric objects, we will have obviously more signature features to consider them. And then when it comes to the different scales, this was why I have highlighted the need of having relative values rather than the absolute values. For example, the dimensional ratio. If you think about the dimensional ratio, right, we can consider it to be a relative value feature, because it doesn't matter how big your object is. We are only looking at the ratio between the length and the width and the height, right? So yes, there are considerations in different scales by incorporating the relative values rather than absolute values. And in order to handle the complex objects with different representations, we then need to be able to know there are, what are the possible types of representation to start with, right? So that means in the training data, you got to include more data to help you develop those algorithms. But as long as you have those covered in your training data, you will be able to come up with the corresponding invariant signatures for that particular type of parameterized object. I hope I answered those questions.
Excellent. Thank you, Johnson.
Thank you.
And we had 2 other questions that Pingbo has already answered online. If there are any other questions, feel free to unmute yourself and ask, or just type it. We have a few more minutes left. And if there are any other questions, I guess we can conclude the session. Perhaps you can reach out to both of the speakers via email. Oh, okay. Q&A. All right. We have question for both of the speakers from Vincent Kyan from Singapore. Regarding the beam generation, what are your thoughts on using multimodal data, graphical and non-graphical, from different sensors, such as mobile and terrestrial laser scanners, to generate a graph or IFC-based representation of information toward 3D beam reconstruction? What's the impact on beam accuracy and compared to point cloud generated beam model? Would you like to take this?
Yeah, I can
Johnson?
try.
Yeah, Pingbo.
Yeah, I can try. Yeah, if I understand the question correctly, the question is about how multiple sources of data could improve the quality of the generated build information model. Then, first of all, I would have to say I don't know there is a reliable way to measure the quality of build information model. Because for the semantics, if you say something is a door, and the door has many different meanings, including the frame, or just look at the door itself, and for different domain, those semantics, like using the same term referring to different things, is very common. If we look at the geometric accuracy only, it's a much easy problem. But if we look at the combination of the meaning of the geometry and the material property and other things combined together to say, of course, if we got more information from sensor data, for example, we have an embedded concrete sensor to measure the property of the concrete, then we can updating the real-time condition of the concrete and get a more reliable understanding about the concrete structure performance. But how to measure the quality of that updated model with the additional information from the embedded sensor, in addition to laser scanning data, I would say we need to have a more reliable measure. And my general thinking about how to measure the quality of information, it's backtracking. Backtracking means we need to look at the decision reliability based on the information to say, okay, if we have more information and if we have more reliable prediction from the model, and how that's going to support a more reliable decision making to reduce the risks of having consequential effects, such as the collapse of the structure during the construction, or to have the misunderstanding from some workers in the field to do something too early or too late. Then we need to have those measures about the decision reliability before we talk about the information quality. That's my understanding. Thank you.
And I would like to add something too. So obviously, Professor Tang is the world best expert on the terrestrial laser scanning. So that question was right to Professor Tang. But I can speak from the the FC representation perspective, because if you remember in the presentation I've shown, when we represent a 3D object, such as cone frostum shape, in the FC, we don't really represent the circle as a real circle, right? We represent the circle as approximated polygon, in which case we used a hexadecagon, 16 points, to represent the circle. So I guess my comments will be, this really depends on the level of accuracy needed in the application. And when it comes to, let's say, collecting the image data, which we do have some similar experience working not directly from images captured on the site, but from the 2D plans. Because in a lot of the agencies and the companies, they are still heavily using the 2D plans to manage the projects. But we are in the transition from the 2D plans to 3D models. But because there is a huge amount of data, it will be very expensive, right? It will be expensive to really create the models manually from the 2D plans. So in our lab, we actually developed algorithms, and it's called pattern pending technology that can semi-automatically process the 2D plans, like the different views, the set view, elevation view, and the bird's eye view of each object, and then reconstruct the 3D representations from that. And then after the 3D representation, and I think this was what this question from Vincent was asking mainly when it comes to the IFC representation, right? So after you have, let's say, after you have the point clouds, because the way that we process those 2D plans, we first converted them into images from vector-based image, from raster-based image to vector-based images. And then from the vectors, from the vector-based images, we reconstruct the 3D shapes, right? But then when it comes to the accuracy, and I think I would like to echo Professor Tang's comments, suggestion earlier, that I think it depends on your real application scenario. You may need to do backtracking, evaluation, and iteratively improve your algorithm to make sure that it is satisfying the needs of your real project. And back to the example that I have mentioned earlier. So our algorithm in converting the 2D plans into 3D models, after that the results were generated, it was mainly in the point clouds format, right? And then we convert the point clouds into the FC. And at the beginning, however, the FC model was just one entity representing the whole project, let's say the whole bridge. And gradually, we have developed also algorithm that can segment that bridge into, let's say, bridge piers and bridge stacks and different components. And also, we keep on working on algorithms that will be able to pull out other semantic information from the bridge plans, and then enrich the FC-based bridge model with those semantic informations. So, again, back to Professor Tang's suggestion, I think we already started implementing some of these, right? Iterative improvement. But ultimately, again, my point is it depends on the accuracy needed. You may need 16 points to represent a circle. You may need 32. You may need 64. So I hope that helps.
Yeah, thank you. Thank you, Johnson. Thank you, Pingbo.
You're
And
welcome.
I guess we're at the end of